Well, this was mentioned. I'm Yael Glazer. I'm a researcher at the University of Texas in Austin, and I'm really thrilled and honored to be here today to talk about this very important topic of water. Oh, good. My slides are up there. Excuse me. And I'm excited to share a little bit about the energy-water nexus, is what we call it. We use energy for water, water for energy. We heard yesterday that we have plenty of water, but it's not where we want it, in the quality we want it, at the time that we want it. And guess what? You need energy to make it get to where you want it, at the quality that you want it, etc. Okay, so I'm going to talk pretty fast. I see the time as well. I only have 20 minutes to cover a lot, so bear with me and hold on to your hats. Thank you very much. Okay, I wanted to also contextualize it for Spain, because I think that we're here, we might as well talk about it. And I found some numbers for y'all. So energy for water and wastewater treatment is about 4.5 terawatt hours. That doesn't need to mean anything to you, but it's equivalent to 1.3 million homes, the amount of electricity needed for that many homes annually. So that's how much energy is required to treat the water for water and wastewater treatment in this country. So just keep that in mind as a number and just an idea of how we use energy for water. So as I mentioned, I'm going to talk about water for energy, energy for water. I'm going to talk about the constraints that we're seeing in these systems, cover some trends, and then summarize it with some technical and non-technical solutions that we have available to us. So we'll go right into it. Okay, so what do we mean when we say the energy-water nexus? Inevitably, it means that energy and water are interrelated or interdependent. When we use one, we're inevitably using the other, and they're inextricably linked, okay? So when we use one, we're using the other. I think it's important to acknowledge a truth, which is that water, which we've heard many times, water is life. Water is essential to life, and energy is the quality of life that we've become accustomed to in the developed world. Our access to energy really is correlated with our wealth, so keep that in mind as well. And they really are the two most critical resources that we have. I want to also point out that as a result of droughts, we have seen civilizations collapse throughout history. Anytime there's issues around droughts, that means we can't grow crops, and then that leads to famine, which leads to collapses in civilizations. And it turns out this, we don't hear about it sort of in the same way today, but we are seeing human migration happening across the world, resulting from issues around droughts and flooding and severe storms and things like that. It's estimated that something like 32 million people annually are displaced from their homes, usually within their own countries. But I think it's important to keep that in mind as well, that these are very impactful even today in terms of human migration and the rest of it. So let's start by talking how we use water for energy. Water for energy, we use it in a variety of different ways all along our energy supply chain. In our extractive industries, think about coal and uranium mining, or natural gas and oil extraction, which is something that I think a lot about being from Texas. All of these things require water. And so in Texas, we have a lot of what's called hydraulic fracturing. And so when we do that to drill, hydraulic fracture, and complete these wells, we use a tremendous amount of water. In addition, we have this wastewater that comes out of there that needs to be managed in some way or maybe even treated. So it turns out that water and wastewater management in the oil and gas sector is a really big part of that industry. We use anywhere from 1 to 10 liters of water per liter of oil, so just to put that number into context for you. We also use water for our energy crops. So in the United States, we grow corn for corn ethanol. We also have biomass for fuel pellets. Irrigating corn is estimated to be anywhere from 500 to 2,000 liters of water per liter of corn ethanol. And to put that into context as well, it's 30% less energy intensive, dense than oil. So it's not even a one-to-one when we're talking about that. And as we've covered, there's the issue of nutrient runoff from the various agricultural chemicals and fertilizers that we use. That goes into our Mississippi River, down into the Gulf of Mexico, causing those hypoxic regions that we'll talk more about as well. We also use water very directly in our hydroelectricity. If you do not have water in your reservoir because it hasn't rained enough because you don't have enough snowmelt or because it's over-allocated, guess what? You're not going to be able to produce as much power as you once were able to. And in fact, we're seeing that in the Hoover Dam, which is in the southwest United States. This is showing you a picture of Lake Mead, which is the reservoir behind the dam, showing you, you can kind of see those, what we call bathtub rings, where the water level used to be, but is no longer because of the fact that the area is getting drier due to climate change. We're over-allocating the water there. We're able to produce less power as a result over time. We use a lot of water for thermal electric power plants for purposes of power plant cooling, and also for boiling water to create the steam to drive those turbines and generate electricity. In the end, we use about 60 liters of water and consume about 4 per kilowatt hour of energy or electricity that's generated, which means in the United States, we use about 40% of our water withdrawals just for the purposes of producing electricity and power plant cooling. More recently, we hear about hydrogen production as being sort of this, next step to helping us decarbonize the hard-to-abate sectors. But, we talk about emissions related to hydrogen and whatnot, but what I don't hear talked about is the water requirements of hydrogen. I don't hear it talked about nearly as frequently, even though steam methane reforming and electrolysis, the two main methods currently to produce hydrogen, both require water, and electrolysis requires it at a very high quality. So keeping that in mind as well. We also use water for transporting our fuels. So think about inland waterways when we have to take ships and barges downstream, carrying things like coal and oil and a variety of other things. You need to have water in those rivers. It seems like obvious, but maybe you don't think about it every day. If you don't have that water, you're not going to be able to move those ships and barges downstream. Let's talk about the ways we use energy for our water system. And so really here we have two options. We have to either bring the people to the water or the water to the people if you live inland. And along the way, as we've discussed and we'll continue to discuss, we want that water to be clean and safe to drink. And of course, when we discharge it, we want it to be safe for the environment. And hopefully you picked up on everything I just said, that means energy is required. And so we end up using a tremendous amount of energy for this whole system. We use energy in our water system for conveyance, for pumping, treating, chilling, heating, and pressurizing our water. In the United States, 13% of all of our energy use annually goes to these purposes of treating, distributing, heating, and all the rest of it related to our water system. Okay. So, in addition, as our wastewater treatment standards tighten for many of the things that we discussed that are getting out of the water system, we'll notice also that we'll have to impose more energy requirements for our water treatment. We can talk more about that later. And also, as we use water that's more readily available, we have to dig deeper or desalinate, and all the rest of it. That as well is going to add to the energy intensity of our water system. Okay, so hopefully you've picked up on the fact that these systems are connected, which means there are going to be constraints in these systems. So as I mentioned, one system could put constraints on the other. And that can be scary, right? You're thinking about, oh no, well, you're using one thing in one system and now it's impacting the other. That's a lot to deal with. But I want to also point out this is a good news story as well, because that means if you mitigate issues in one system, you're going to see mitigation in the other most likely. So let's talk about the various ways that these systems are constrained. When there are extremes in our water system in any direction, whether we're talking droughts or floods or heat waves or freezes, all of these weather and water extremes are going to impact our energy system. I'm going to give you guys a variety of examples to kind of illustrate this. Heat waves can impact the ability of power plant cooling. River water temperatures during heat waves are going to be hotter than average. Oftentimes, water levels are also going to be lower. Power plant cooling also won't be as efficient, so requiring more water for cooling. Our environmental standards and regulations for thermal pollution of the discharge water could then prevent from doing any cooling at these power plants if the starting river water temperature is already too warm, so you're running into an issue right there. So for an example on this, in 2003, Europe had its worst heat wave up until that point. Many of you maybe are familiar with this. In the end of that summer, 70,000 people had died, mostly among the elderly. It was a horrible situation. France was especially hard hit. They have about 80% of their electricity from nuclear. A lot of their nuclear relies on river water. And so they had an issue where they had to curtail power, so they had to turn off some of their power plant generation because they didn't have either they didn't have water in the river or the water was too warm, meaning that they couldn't do that. And so they actually ended up asking the government for sort of a stay on that regulation to allow them to provide power. Even with that stay, they had to curtail power for about 15% for a span of 5 weeks and had to cut power production to outside of France. In addition, as we heard, when these things happen, we have crop yields that also decline, meaning that you're not going to produce as much food, which, by the way, food is energy for people, so keep that in mind as well. Let's talk about freezes. Water can be too cold, and that's a problem too at times. Believe it or not, the example I have for you today comes from Texas. So we had a freeze during Winter Storm Uri in February of 2021, resulting from a polar vortex event, which actually impacted most of North America. So it hit Canada, the United States, and parts of Mexico. For about a week, we had sub-zero temperatures. So for about a week, we had lower than 0 degrees Celsius in Texas, which is almost unheard of. We have freezes every once in a while, but not for that duration. And so why was Texas especially hard hit? It's because we have mainly 3 grids in the United States: the West, the East, and Texas. And it turns out they're not well connected. In fact, they're not connected really in any meaningful way. So that meant we couldn't call on our neighbors for power as our power plants started to fail. So what happened was, our power plants started to fail. We had a water pump that froze, turning off some of our nuclear power generation. We had ice on our wind turbine blades. We had snow covering our solar panels. We had frozen natural gas gathering and distribution lines that made it very difficult, in fact, impossible to move natural gas from the wellheads all the way to the power plants to generate power. And so in the end, we had 28 gigawatts of power that was not being met during this crisis in a state that provides 85 gigawatts at peak demand. So a huge amount of power was not available. And keep in mind, everyone was calling on power, right? Because they're like, I'm very cold. We're not used to that in Texas. So we were running our heaters pretty much around the clock. This meant that 2 out of 3 Texans experienced a power outage during this time, anywhere from a couple hours, or in my case, was 2.5 days, in a time where really we couldn't get out. Texas, I don't know, I can't stress this enough. We are not set up for this. We don't know what to do. So we couldn't really even leave our homes in this situation. What was extra difficult with this is that we started with cold, frozen water that led to this power crisis that then led to more water crisis. So when this happens in Texas, what we do is we drip our faucets. That's to help prevent any damages to our water pipes and leading to damage in our homes. So everyone across the state was pulling water from the system. And at the same time, unfortunately, a lot of people, as you can see in the picture, the pipes burst, and so even more water was being demanded. That led to the pressure in our water system dropping. And by the way, at the same time, a lot of the water systems lost power, meaning they couldn't treat and distribute more water for this whole system. So our pressure dropped. A lot of people experience this as no flow or low flow of water into their home. When the pressure drops, immediate boil water notice. So about 2,300 boil water notices were issued across the state, probably the largest boil water notice in American history. So keep that in mind as well. And I just, as someone who went through it, I don't know how to express how annoying, at the very least, it is to be told to boil your water when you don't have power. So that was not fun. But anyway, just to give you guys an epic example of the energy-water nexus that we had to live through. Okay, let's talk about droughts. Severe lack of rainfall and subsequent heat waves in May of 2022 in Europe left a visible toll on Europe's waterways. Again, if you don't have the water in those rivers, you're not going to be able to move stuff downstream. So I think that's the main takeaway here. And again, with these droughts, led to lower crop yields as well. We also have issues around flooding. So flooding causes issues in our energy system. Here's an example from August of 2017 during Hurricane Harvey. It hit a lot of the Gulf of Mexico, but specifically in the mainland of the United States was Texas and Louisiana. It led to catastrophic flooding because the hurricane basically lingered over Houston, dropping an entire year's worth of rain in a span of 4 days on Houston, and all kinds of horrific things were going on as a result of the flooding. including the fact that 500,000 cars were flooded. So this is just a picture of one area where they put the cars out for pasture. So 3 fields about this size were just filled with cars. We also had an issue where Houston is where we do a lot of our oil refining. About a quarter of the United States capacity in oil refining happens there. That meant higher fuel prices at the pump, even though crude prices were actually staying about the same. Let's talk about some of the trends that are going to impact our energy and water system. I'm going to move real quick because we're going to talk about them, I'm sure. Population growth, more people, more energy and water. Economic growth, the wealthier we get, the more energy we're going to use, the more water and higher quality water we're going to expect. And also, climate change is going to exacerbate this situation because we're going to need more energy. As our climate changes, it's going to distort our water cycle, which will require more energy. And as long as we're using carbon-based energy, we're going to see this pathway kind of continue in a positive feedback loop. Okay, what can we do about it? I'm sure that's a thought you guys have on your minds. So the good news is we have technical solutions and non-technical. For our water system, we could try to find treatment methods that require less water, less energy, or use more degraded forms of water for tasks that don't require potable or fresh water, as we're kind of hearing already talked about. Wastewater treatment plants are full of organic matter, as we heard, and if sent through an anaerobic digester, will mean that we can generate biogas that can be used to offset some of the electricity requirements at those facilities. And in addition, many water pumps are oversized, and so if we just used variable speed drives for those, we could save anywhere from 30 to 50% of our energy for purposes of pumping. We also have many options in our energy system. We can move towards water lean energy production. Solar and wind come to mind. Considering more water lean power plant cooling options, you can do closed loop cooling, you can do air cooling. Of course, everything comes with trade-offs. We can also use seawater for power plant cooling if that's available to us, if you're close enough to do it. Of course, moving away from corn ethanol might be a great option if we're worried about our water use. And also keeping in mind that water heating, as I mentioned, is a big contributor in the amount of energy that we use for our water system. In areas where solar thermal water heating is an option, I'm thinking areas like the southwest of the United States and in Israel and Lebanon. These are places that use those tanks on their roofs to basically heat the water using the sun, so you can offset some of that. Tankless water heaters use less energy than their tanked counterparts, so that's another great option. We can also use smart meters and smart devices for our water and electricity systems to help the household level understand their water and energy use better. It helps us detect leaks, excessive lawn watering, and also help us adjust thermostats and lighting when you're not home and things like that. I think one thing that doesn't get talked about enough on that is the security aspect of it. On a personal level, not everyone wants their utilities to know when they're home, what they're doing, and how they're using things, so that's a concern. And on the utility level, all of these sort of connected devices means one weak point for hacking, so keep that in mind. That's something I think we should discuss also. We also have policy as a lever, so that's a non-technical solution. These days, lots of policies around emissions associated with our energy system. I don't hear, again, a lot talked about the water policy around water and connecting that as well. We should take that more seriously, I would say. And again, a great example of that is how we don't hear a lot about the water implications of hydrogen. Also, we have markets, so that's a non-technical solution that can help us here. And so this is where I'm going to kind of wrap things up. Water and electricity markets that are based on supply and demand, time of use, and scarcity can help us out here. So we can deploy things like smart meters and technologies to help with that. And generally speaking, the price of water is extremely cheap. I mean, we're really not paying the full cost of water. I think that's not news to anyone in this room. And so let me give you an example about what it would mean if we go towards real price for water. So Israel is a place where water's always been sort of a central issue and taken very seriously from the start of the country. And in 2008, Israel was experiencing a particularly challenging drought, so they implemented a lot of conservation projects and programs and consumer education programs and campaigns on ways to save water across the country. And it was pretty successful, about 8% drop in water usage across the country, and that's considered, I would say, a success. But it was not enough. They still needed to save even more water. So what they did was they announced that everyone people in the cities, agriculture, industry, they're all going to pay the real price of water. That's it. We're all going to pay what it actually costs to treat and distribute this water. And you know what happened? They doubled their savings. So it turns out if you make people pay the real cost of water, they're going to figure out how to use less of it. And so I think that's an important thing to keep in mind. Now, we have to balance that with equity. I'm not suggesting that people go without water. Water is life. We need it for life. But maybe kind of thinking about it that way would be an important thing. So bottom line, water and energy are inextricably linked. Hopefully I've communicated that. And we must work to ensure the future generations will continue to have access to clean and affordable forms of these two critical resources. Thank you very much. Appreciate your time.